Hello, welcome to Algebra 1, lesson 4.5. Today, we're going to talk about transforming some of these um, exponential functions that we've been looking at. And let's get back to the beginning here. So lesson 4.5 is going to be in Module 4, page 5 of the online textbook. And this is for course Algebra 1, ninth grade. Transforming exponential functions happens when you modify the equation that you originally start with. Remember, our basic exponential function looks like a graph where it's swooping upwards, going up a mountain, right? We can change the way it looks by altering the equation, right? One of the ways we do that is with a multiplier. And here I have for you, it says f of x equals a times b to the power of x. So that a in the front is called a multiplier. And depending on what the number is for that a, depends on how the graph changes or adjusts or transforms. So if a is negative, all of a sudden the graph flips. You get the mirror image over the x-axis. If a is greater than 1, then the graph is vertically stretched. It's like someone came and reached and grabbed that top part of the graph and pulled upwards on it. And everything is going to shift based on that. If a is less than 1, but not negative, so between 0 and 1, it's going to still be the swoosh upwards, but instead of someone pulling on the graph, it's going to vertically compress. It's going to be as if somebody has their hand on it and is pushing downwards, kind of squishing the graph down, okay? So those are the three ways that this A can transform the graph. However, you can actually combine them. Like you can have a negative, not just a -1, but you could have like a -2, and that would have the reflection as well as the vertical stretching. Let's start off by graphing y equals 2 times 3 to the power of x. Let's do this by creating a chart, right? Just like we've done in the past. So here I have our chart that has been started. And so we're going to plug in -2 to where this x is. So it's y equals 2 times 3 to the power of -2. Now, initially, your gut reaction is generally to start off by doing 2 times 3, but wait a second. We have to remember our PEMDAS, okay? PEMDAS tells us that first we have to do parentheses, right? Second is exponents. Now, we usually jump straight to multiplication and division because it's not too common to see parentheses or exponents. We do see a number of parentheses, and I think that for the general population, it's pretty well understood that when you see parentheses that you have to do that first. But it's easy to miss these exponents. And that's what we need to pay attention to is the exponent. We need to do the exponent first. So we're going to start off by just writing the 2 here so that we know we'll do that one later. We need to do the exponent first. So 3 times a -2. Let's look at the negative first. What does that mean? Well, that means it needs to switch. And we need to find its reciprocal. And remember, this is 3 over 1. The 1 is implied. So what's the reciprocal of 3 over 1? It's going to be 1/3. Now the squared gets applied to both the numerator and the denominator. Okay, but 1 squared is still 1. So then 3 here is squared. All right, so this is 2 times 1/3 squared. Let's look at this. Y equals 2. Let's create a fraction times 1 over, what is 3 squared? 9. Well, that's the same thing as 2/9. And I cannot reduce that anymore. So 2/9. That's what I've got. Let's look at this next one. Y equals 2 times 3 to the -1. Well, that's 2 times 1/3, which is 2 over 1 times 1 over 3, which is 2/3. So let's put 2/3 in here. All right, now let's look at y equals 2 times 3 to the power of 0. Well, what is anything raised to the power of 0? Well, it's 1. So in this case, we no longer have the 0 always being at the point of 1 when it crosses the y-axis. So because we have that multiplier that's going to change it. So you can see how this vertical stretching is affecting everything in the graph. It's pulling it up. So every input that you have is going to have a higher output, as if the graph has shifted upwards. So instead of 1 here, we have 1 times 2, which is 2. All right, so 2 times 3 to the power of 1 is simply 6. And 2 times 3 to the power of 2 is 2 times 9, which is 18. Wow, that is getting big fast. Let's see if we can look at what this looks like on a graph here. Trying to erase some of these so we can see the graph better. All right, so let's go ahead and see about plotting some of these. 0, 2 is easy enough. I'm going to plot that one. 1 is halfway between 0 and 2, so this is 1 right here, 1. And we need to go up to 6. 1, 6. And then 2, 18. 2, 18 is going to be all the way off the chart, so I can't really graph that one because the chart, the coordinate plane picture that I have here doesn't show 18. But let's look at negative 1. Negative 1 is right here, negative 1, halfway between the 0 and the negative 2. And it says 2/3. So it's not quite 1. 2/3 is a little bit more than half. So it's not quite 3/4, but it's about right there. Okay. And then negative 2 is 2/9. Remember, this is 1 here. So 2/9, this is negative 2, 2/9. That's definitely going to be less than halfway, and that's going to be pretty close to 0. Let's try it there. This is just telling us that it's the number 1. That's not a point there. Let me write it on the other side so we don't confuse it with a point. Number 1. All right, so let's see what this graph looks like. When we draw the line in and connect all the points, we can see that this graph increases in its height. It's going up a lot faster than the previous ones that we looked at. They definitely went up fast, but this one is moving at a faster rate, a faster clip, a faster pace, right? So let me finish erasing some of these notes here. What would that graph look like if it didn't have the 2 multiplier at the end? Because I want to compare our graph of 2 times 3 to the power of x and just 3 to the power of x. What's the difference? Well, let's see. This green one is 3 to the power of x. The blue one is 2 times 3 to the power of x. So this blue one has a multiplier of 2. 2a is going to equal 2 in our equation of f of x equals a times b to the power of x. Okay, so you can see how we've taken the green one, reached on the top of it and started to pull up. And as you're pulling up on it, it's moving up. Each position, X position, is going to move up a little bit higher. Okay. And that's exactly what that says. As the multiplier increases, this vertical stretching becomes even more noticeable. So I want us to take a look at what is 5 times 3 to the power of x. What is that going to look like? Because the bigger the multiplier number is, the more it's going to stretch upwards. The faster it'll go up. So here's the purple one. And you can see with this purple one, if we move from the original to the one with the 5 multiplier, look at the difference between those, between where it is on the green one to the purple one, and you can see it's been pulled up even further. Well, is the only way to transform it through a vertical stretching? No, there's going to be multiple ways you can make these transformations on your exponential functions. So one of the things we looked at with the multiplier was the vertical stretching. There's also vertical compression or squishing down. And then there's reflection where it flips over the x-axis. So the value of the A will tell us what's going to be happening with the graph. So if it's negative, we get that reflection. If it's greater than 1, we get the vertical stretching. And if it's less than 1, but greater than 0, you're going to have it vertically compress or be squished down. We're going to look at it. So here we see the graph of y equals 3 to the power of x in green. That's the one we've been kind of sticking with this whole lesson here. But here, this is 1/2 as the multiplier. And you can see it's as if someone has taken the green one and just kind of pushed down on it or compressed it. So we can see that each of the points on the green graph gets further down in the blue graph, right? So it's pushed down when you have a fractional multiplier. And here is the vertical stretching that we looked at in the last slide. We saw the green getting pulled up. That's what this purple one is. That's with a multiplier of a whole number 2. And the blue one is with the fraction of 1/2. Because I wanted you to be able to see both of them together. Now, there's still one more way that this multiplier can transform our exponential function, and that's going to be with a reflection. We talked about it will reflect over the x-axis. So let's look at what that's going to look like. Here in the green, you have y equals 3 to the power of x, just like we've been looking at so far. And then this is, oops, I didn't put the right thing in there. It should say -1 times 3 to the power of x. Now, you'll generally see that written as -3 power of x, because this x in this case is only applying to the 3 and not to the negative. In order for it to apply to the negative, it would need to be in parentheses. So -3 to the power of x is the same thing as -1 times 3 to the power of x. Okay, you have to be aware of that, not only for in your calculator, but when it's written on paper as well. So in the red, we see this multiplier, how it has flipped. Here's our x-axis right here. And you can see that every point up here on this one is reflected down below it. It is a mirror image, okay? So that is one way that you're going to see reflection. That's anytime you have a negative as a multiplier. Now, you don't have to have just the multiplier doing one thing at a time. It can do multiple things at a time. So here we see in purple, the vertical stretching of 2 times 3x to the power of x, rather. And so that shows the vertical stretching of the original graph. Well, we could, if we, instead of having a +2 as a multiplier, had a -2 as a multiplier, it not only would continue to stretch it just like it did before, but then it would also have the reflection. And so the transformation that happens for -2 times 3 to the power of x is there's 2 types of transformations that happen there. There's a reflection as well as a vertical stretching. Okay, so you get both of those in this. The purple one is simply a stretching because it just had the multiplier of 2, and the red one is just a reflection. And that's because it simply had the negative multiplier. With the number of 1, you're just applying the negative to it. There's no stretching or compressing happening. It can also happen, you can combine reflection and compression together to get a compressed graph that has also reflected. You should be able to tell what's happening based on looking at the graph, but also based on the equation that you have in front of you. It should give you all that information. All right, so one thing that this material covered that they did not have a vocabulary word for on page 1, but is important for you to understand is the word asymptote. So an asymptote is a line where a curve is going to approach it, but never actually touches it. Did you know if you're sitting in a chair right now, you're not actually touching that chair, you're hovering over it so minutely that you can't tell? It's true, look it up, it's physics. But the atoms that our bodies are made up of have a very dense nucleus where most of the matter is located. And the rest of the atom is empty space with these itty bitty little electrons that are zooming all around. And the electrons have a negative charge and they repel things from them. So when atoms get close together, they actually are repelling one another. So as you flop down into a chair, you're not actually touching it, you're hovering over it. And that's kind of how asymptotes are. This line wants to get, our graphed line, our curve, shown in blue, wants to get onto this horizontal asymptote, vertical asymptote, or oblique asymptote. It wants to get there. It wants to sit in the chair. But those electrons just aren't going to let it actually touch it. So it just keeps getting closer and closer and closer and closer, but it never actually touches the line. Okay, so an asymptote is an imaginary line. That's kind of why it's dotted here for us. It's not because it's greater than or less than, but it's imaginary. It's implied that our curve will get closer to, but never actually reach. And that's as it approaches infinity. So these are continuing on forever and ever in both directions, right? And so this one is approaching an asymptote. This one is approaching the asymptote, and over here is approaching the asymptote. Now to our eyes, it looks like they touch, but they never do. If you go in and you zoom in and you zoom in and you zoom in, eventually you'll see that there is still space between the asymptote and the curve that is being graphed there. If you use a computer program, if you hand draw it, you might not do it as exactly because the measurements get so minute. It's so minute. But you can see a horizontal asymptote means it goes left to right, right? Vertical means it goes up and down. Oblique means it can go anywhere in between the two, between horizontal and vertical. Anything in between those two is an oblique asymptote. And it's not just one asymptote per graph. You can have multiple asymptotes in a graph. In this graph, we have two asymptotes, a vertical asymptote and an oblique asymptote. This is multiple vertical asymptotes in this graph. So you're not relegated to have just one asymptote. There can be a plethora of them. Just know that when you see a dotted line like this on a graph, it's usually going to be, unless it's also shaded in like we were doing with our inequalities that we were graphing, if it's just a line with other curves or other lines drawn in, then it's probably an asymptote, and that means that it will never be touched by this graph here. Now, the asymptote that we see the most common in what we're working with, exponential functions, is going to be the horizontal asymptote. As our horizontal, this one shows decay here, and it's approaching the asymptote B. And we'll get into in future lessons how it's B here instead of the x-axis, because all the ones we've looked at so far have been the x-axis being the asymptote. However, it can change based on our transformations and how we transform the equation. So as this curve, this decay curve is getting closer and closer to this asymptote, it never actually is able to approach it. It never is able to touch it. So that's what an asymptote is. All right, so now we're supposed to match the graph to its equation. So we have a graph here, and we see this is going to have, based on what I know that f of x equals a times b to the power of x. Well, I know that 0 is crossing at 1, so that gives me some information. Well, no, it's not crossing at 1. Here's 1. So it's crossing at 1/2. That gives me some information. I see that this is an growth, exponential growth, not decay. So it tells me that B is going to be a whole number, not a fraction. B is a whole number. And this was compressed. So A, that's why it's down here at 1/2 instead of at 1. So A is going to be a fraction. Okay, so which one of these is B a whole number and A a fraction? C right there. So this is C. All right, let's look at the next one. Number 2, I see this as a reflection. Reflection. Okay, it's crossing at the 1. So A didn't vertically stretch or compress it at all. So A has got to be 1, but it may be a -1 because it's a reflection. And I see that it is, if this were not reflected, would that be growth or decay? Well, it's growth, which means that B is going to be a whole number. So we need a whole number that has a negative number, negative A, negative multiplier. It looks like it's going to be right here, D. D. All right, so let's look at this one. Already off the bat, I see it's crossing at 2, and that tells me it's been vertically stretched because it's no longer crossing at 1. Okay, so I know that my A, if I vertically stretch something, has to be greater than 1. Greater than 1. I could have used the greater than symbol. Don't know why I didn't. Okay, so A is greater than 1. I see that this is decay. So this is going to be a whole, a fraction. B is going to be a fraction, and it's not reflected. So I want my A to be greater than 1 and my B to be a fraction. Already I see it. A is greater than 1 and B is a fraction. So this is graph A. So A, C, D, this should be B, but let's just double check it to be sure. I see it's crossing at 1, so it's not going to be stretched or compressed at all. So A is going to be a version of 1, but it does look like a reflection, so it's a -1, okay? And my B, all right, so B, is this decay or is this growth? Well, the easiest way for me to do that is to say, well, what would it have looked like if it wasn't reflected? Well, it looks like decay to me. So I want B, I know is going to be a fraction. So a -1 and a fraction. Here's -1 and here's my fraction, okay? So B was the correct answer. And I hope you paused that and tried to do it on your own. I know I forgot to remind you, but anytime we have practice at the end, I do encourage you to pause it and try it on your own at any time throughout the lesson, even if it's not a practice. Feel free to pause it and do it on your own. The more you learn to do it on your own, the easier it will be for you. Here's another practice. Go ahead and pause and come back when you're done. All right, so the question is, how will the multiplier in each of these equations transform the graph? So all we're really concerned with is this number before the B. We don't need to look at this at all. The B to the exponent, not concerned with it. So there's 2 things that are happening here. The first thing that we have is going to be a reflection. Okay. And the second thing we need to see is that A is a whole number. And so that means we're going to have a vertical stretching. So this is both reflected and a vertical stretching. All right. Again, we're not concerned with this at all. We're just looking at this. There's no negative, so there's no reflection, and it's a fraction. So this is a vertical compression or squishing. All right, not interested with this, doesn't matter to us. This has 2 aspects. It has the negative and it has the fraction. So the negative means we're going to have the reflection. And the fraction means we're going to have a vertical compression. Okay, here, it doesn't look like we have a multiplier at all, does it? But the only thing we're crossing out and getting rid of is the B and the exponent. So we still have that negative there. What does that mean? Well, that means that this was really -1 times 3 to the power of x. Because remember, when it's -3 to the power of x, the x is only applying to the 3 and not the negative. Okay, so the negative is really applied to an implied number 1 that is being multiplied to it. So we have a -1 as our a, which means that this is just a reflection. All right, I hope you got all of those correct, and I'll see you on the next lesson.